Okay, so today we're going to look at a problem from 2009's AP test. It's a problem with a diver. Man is jumping off a cliff into water, and the cliff is 11.4 meters above the water. And I have a picture drawn here, and you can kind of see that I've simulated the path of the diver. He is going to jump not away from the edge of the cliff, as well as be rising up and down into the water, and the cliff height is 11.4 meters. They also tell me his x direction velocity, dx dt, and they tell me the y direction velocity, dy dt. Okay, so let's take a look at part A. Part A says find the maximum vertical distance from the water surface to the diver's shoulders. This is a maximum y value. And in order to find a maximum y value, we're going to need to take the derivative of y prime, and set that equal to 0. And the nice thing about this problem is we already know the derivative of y, dy dt. We know that dy dt is 3.6 minus 9.8t. And if I take that and set it equal to 0, I will get my critical value, which is going to be 0.367 seconds. I can tell by the path of the diver that this will be the maximum. So now I actually have to find the position of that maximum, and this is a displacement problem where I have an initial position of 11.4 plus the displacement, which would go from 0 to 3.6 or 0.367 seconds, and I take the integral of the velocity in the y direction with respect to time. This is a calculator-based problem, so once I go ahead and do that, I end up with 12.061 meters. Okay, and again, remember that the derivative that they give me, dy dt, is the velocity in the y direction. Okay. Okay, so let's take a look at part B now. Part B says find the time when the diver's shoulders enter the water. Now, when the diver's shoulders enter the water, the position, the y position of the diver will be at 0, so when y equals 0. Let's start off with our y equation here. And if you remember, our y position is equal to our starting point, 11.4, plus a displacement, and our displacement will be in terms of y. So it'll go from 0 to whatever time, and we'll have the velocity in the y direction is what we're trying to integrate. That's my dy dt. And this question asks me to figure out the value of a when the y value is 0. And so if I replace my y with 0, I can begin to solve this equation. But how do I solve this equation? Well, in order to solve this equation, I actually need to do an integral. And so the integral of 3.6 minus 9.8t, the integral of that is going to be 3.6t minus 9.8t squared over 2. And I need to evaluate that as t goes from 0 to a. And this is just a top minus bottom type of problem. So when I plug in a for t, I'm going to get 3.6a minus 9.8, or let's just simplify that, minus 4.9a squared. When I plug in 0, I'm going to get 0 there. I'll just kind of write it as minus 0 as if I plugged in 0. I need to solve this equation for a. This is a quadratic equation, so if I set it up and set it equal to 0 here, I can then either use quadratic formula, I could use my calculator and graph it, or whatever other functions you might have in your calculator. But you solve this for a, and that will be the time that the diver hits the water. Remember that your a value here has to be a positive number. We can't necessarily go back in time. Okay. So 1.936 seconds is my answer here. Okay. Again, we started with a y equation, And we solved that y equation, computed the actual integral, definite integral from 0 to a, and we set that y value equal to 0. Let's go on to C. Part C says find the total distance traveled by the diver. Okay, from when she starts jumping until when she hits the water. So now we know our time interval because we just calculated that in part B. And our distance here, if I was going to write an equation for distance, the distance equation would come from adding up an infinite amount of hypotenuses, and that's going to be the square root of dx squared plus dy squared. And from here, I adjust this formula based on how the function is described to me. This function is described with dx dt and dy dt. That means I'm going to go back to my total distance formula, my summation of an infinite amount of hypotenuses, and I'm going to divide that equation by dt, and I'm going to multiply that equation by dt, and that means I'm going to end up having t bounds here. And remember, my t bounds are going to go from 0 to 1.936. Okay. The rest of this is calculator work. We can kind of make sure you compute all this out, and you should end up coming up with 12.946 meters total distance traveled. Total distance formula again comes from adding up an infinite amount of hypotenuses. You have a starting formula, and then from there you can adjust it based on how the function is described to you. Okay. Let's move on to part D now. And in part D, the problem asks you to calculate the angle at which the diver goes into the water. Now the angle, the direction at which the diver moves into the water, is going to come from our velocity function. Okay, and we have two velocity functions that we have to deal with. We're going to have a direction coming from the velocity in the x direction, and we're going to have a direction associated with the velocity in the y direction. And when I combine these two vectors, the x components and the y component directions, I'm going to get a resultant vector. And that resultant vector is going to represent the speed, and the angle at which those two vectors, or the resultant vector, makes with that horizontal there is going to represent the angle at which the diver enters the water, is his direction. This is a simple right triangle trig. It's an inverse tangent problem. We want to make sure that our inverse tangent angle comes out to a positive value. Okay. By the way, the numerical values for the velocity in the y direction and the x direction will be at that instant when he enters the water, which is going to mean at time equals 1.936. Calculations on this would be that theta equals 1.519 radians. You could move that into degrees if you'd like, although radians is more appropriate. Hope this helps. Have a great day.